Hello, my name is Alex McDonough. I'm a fifth-year grad student at Brown University, and today I'm going to be telling you about a higher dimensional sandpile map. So my plan for this is first I'm going to explain how to define chip firing for a large class of representable matroids equipped with a multiplicity function. And if you don't know what chip firing is, it's fine. And in this context, we're going to get a generalization for Kirchhoff's matrix-tree theorem. Again, if you don't know what that is, it's all okay. I'm going to give a family of combinatorially meaningful maps that are akin to bijections, but they're no longer between sets of equal size. I'll explain more what that means. And the proof is going to use a geometric construction that gives a periodic tiling of space, which means that if you stick around, you're going to see some pretty pictures by the end. Finally, I'm not going to assume any prior knowledge beyond what one would expect to see from like undergraduate math majors. All right, let's get started. So first I want to tell you about representable matroids. So in general, a matroid is a pair, E, B, where E is the ground set and curly B is the set of bases. And B is some subset of the power set of E, and it has to satisfy some rules. But I'm not going to explain exactly what those rules are because we're just going to be working with representable matroids. So for representable matroids, you're going to start with a matrix. And the ground set is going to be the columns of the matrix. So in this case, V1 through V4. And the bases are the maximal linearly independent subsets of E. So any set of column vectors that are linearly independent. And in this case, any three of the column vectors are going to be linearly dependent, but any two of them are linearly independent except for V1, V4. So those are going to be our bases. And one nice thing about this definition and working with representable matroids is this is exactly the same definition of bases that you'd work with in linear algebra. And the size of each basis is called the rank of the matroid. They're all going to be the same size. You may have actually proven this in linear algebra class. In this case, our matroid is going to be rank 2. And we're going to denote this by R throughout the talk. So we have the same matrix. These are the things we've already kept track of. And we're going to introduce a new concept called basis multiplicity. So for each basis, the multiplicity is going to be the greatest common factor of the determinants of all rank by rank minors of the matrix restricted to B. So for example, V1, V2, we're going to restrict to the first two columns, and we're going to look at all of the 2 by 2 minors. So in this case, there's 3 of them. Find each of their determinants, and you'll find that they have GCF of 1. Similarly, the multiplicity of V1, V3, find these 3 determinants, you get another GCF of 1. These 3 determinants, you have GCF of 2 this time, and then the final 2 are 3. And I encourage you to pause the video and prove to yourself that this is in fact true, because I have to go fast. Got 20 minutes. But this idea of a multiplicity function is related to the theory of arithmetic matroids. It's sort of a baby version of it in a very particular case. Arithmetic matroids can be a lot more general and aren't necessarily representable. And they actually give some multiplicity function to every subset, not just the bases. But this is related to the like most general or most the opposite, most specific definition when you're working with arithmetic matroids. All right, so we have M on the left that we've been working with, but we got this new matrix D on the right. And something cool is that M and D represent the same matroid with the same multiplicities. You can check that if you'd like to. And in fact, their rows generate the same lattice. So if you take all of the integer linear combinations of the rows of M and all of the integer linear combinations of the rows of D, you're going to get the same vectors in Z4. So that's pretty cool. And this is no coincidence. So whenever you have a matrix M such that the first R vectors have multiplicity 1, then there's an algorithm by Pagaria that allows you to construct a matrix D that has these same properties as M, but has this very nice structure where, first of all, it has rank many rows, and secondly, the first rank many columns are going to be the identity matrix. So we're going to call a matrix of this form a standard representative matrix. This is going to be a very important definition for what we work with for the rest of this talk. But what I want you to keep in mind is whenever we say something that's true of a standard representative matrix, you could also start with any matrix that has a multiplicity 1 basis and then convert it to a standard representative matrix. If your multiplicity 1 matrix isn't the first R columns, you can just rearrange them and you can do it anyway. So this is going to work as long as we have a multiplicity 1 basis. And if we don't, stuff gets weird. I'm not going to talk about it in this talk. All right, we have our standard representative matrix. Here's an example of one. And we've got this very special matrix that I'm going to be talking about called D hat. So to get D hat, what we do is we take negative n transpose, where n is like the part of D that isn't the identity, and then we're going to put the identity at the end. So it's going to look like this in this example. Definitely pause and think about it if you can't figure out where we're getting this from. These end up being very related to each other, and I'm going to talk about this in the next slide. So the first thing that I encourage you to prove is that the rows of D hat are all orthogonal to the rows of D. So you take a row of D hat, you take a row of D, dot multiply them together, you're going to get 0 no matter what. And that's pretty easy to show. Oxley showed the D hat represents the dual matroid of D. If you don't know what a dual matroid is, you can just ignore that. It's not going to affect things too much, but it's nice to know for people who are familiar with matrices. Next up, if we restrict D to some set of R columns, and then we restrict D hat to the remaining columns, the determinants of each submatrix is equal up to sign. So, for example, we could take the third and fourth column of D, then the first, second, and fifth column of D hat, and these determinants are going to be equal up to sign. And I encourage you to prove this because it's a nice little proof that it's pretty direct, but it's kind of neat how it works out. And the other thing we can do is we can put D on top of D hat, and we get an invertible square matrix of this particular form. And we're going to call this curly D. So curly D, it's going to look like this. And you can come up with curly D uniquely if you're given a D, as long as D is standard representative, which it will be for the rest of this talk. All right, so we have D, we have curly D. Now we have the sandpile group of D. So the sandpile group of D, which is denoted S of D, is going to be Z to the n plus R divided by curly D transpose times Z to the n plus R. Now, what does that mean? That means that it's the set of all points in all lattice points in n plus R dimensional space, where we say that 2 of these lattice points are equal if you can get from one to the other by adding some integer linear combination of rows of curly D. That's all it means. And this is going to sound like a really weird definition if you're familiar with the Sandpile group and chip firing on a graph. I have a video on my webpage that explains exactly where this comes from and how it relates to the graphic version. And so I encourage you to check out this video if you want to understand where this group is coming from, especially if you've seen the Sandpile group before and this all looks very foreign. But you're not going to need to know this to be able to understand the rest of the talk. You can just believe me that this makes sense as a definition. One of the biggest theorems of the Sandpile group on a graph is what's called Kirchhoff's Matrix-Tree Theorem. So Kirchhoff's Matrix-Tree Theorem has a relationship between the Sandpile group and the spanning trees of a graph. But if we generalize this to this case, we get a relationship between the Sandpile group and the bases according to their multiplicity. So in particular, the size of the Sandpile group of D is going to be the sum of the multiplicity squared of each basis in your matroid that D represents. And this theorem is by Duval, Klivans, and Martin. They had a different form of it, and there's a little bit of added generality because they deal with the case where you might not have a multiplicity one basis. But if you convert everything to the matrix version, then it ends up looking like this. And this is called the Cellular Matrix-Tree Theorem because they were dealing with cellular complexes. And if you want to know how this is related, what you can do is take the boundary map of a cell complex with an arbitrary orientation and convert it to a standard representative matrix, and then you get the same sandpile group that they were talking about. But if you, I mean, none of that has to make sense to understand the rest of the talk. This is a theorem that's true. And let's just see a representation of it. Here's a D. The sandpile group, we can get the size by taking the multiplicities of each basis. In this case, it's just a determinant because D has rank many rows. We don't have to take GCFs. And we end up getting 1 squared plus 2 squared plus 3 squared, which is 14. And I encourage you to actually look at the sandpile group of D and see if you can prove more directly that there are, in fact, 14 elements of the sandpile group. One particular case we could look at is where the multiplicity is always 1. And in this case, we say that D represents a regular matroid. And we get this theorem that came by 10 years earlier, that the size of the sandpile group of D is equal to the number of bases, as long as D represents a regular matroid. And this is sort of what happens when you take the graph version and convert it into working with regular matroids instead of just graphs. Matroid theorists love taking things about graphs and then saying, hey, does this work with matroids? And that's most of what we do. So like almost 20 years after that, Backman, Baker, and Yuen defined a family of natural bijections between these two sets for the regular matroid case. And essentially what I'm trying to do is generalize this to the case where you don't have a regular matroid. So I give a series of a family of maps from the sandpile group to the bases such that the preimage of each basis is of size multiplicity squared. And my goal of this presentation is going to be to share these maps. So if you're not quite sure what I'm trying to do, I encourage you to pause the video, think about it, because it's really all on this slide of really what my goal is. And you can think about why I say it's like a bijection. So in order to do this, we're going to need to talk about fundamental parallelepipeds. So given a square matrix, you can take all of the combinations of its linear combinations of its column vectors multiplied by some number from 0 to 1. And the points that can be expressed like this are called the points of the fundamental parallelepiped of M. This is also called the zonotope or Minkowski sum. Some people say that it's a parallelotope in general and parallelepipeds just for 3 dimensions, but I've seen it both ways. The word parallelepiped is really fun to say, so I'm going to go with it for this talk. It's also the one that I used in my paper. And what we're going to do, part of our plan, is each basis we're going to associate with some fundamental parallelepiped. So how are we going to do this? So let me do it by example, because that's how I like to do everything. Here's some matrix D, and we got that curly D is going to look like this, and I put a little line in it to really emphasize where D is and where D hat is. And here's something that's a lot easier to see an example than to explain. So this is a non-full explanation, but what we're going to do is for each basis, to get the parallelepiped, we're going to look at each column and see whether it's in B or not in B. And if it's in B, we're going to put everything below the line and turn it into 0. And if it's not in B, we're going to put everything above the line and turn it into 0. So in this case, the fundamental parallelepiped associated with V1, V2, well, V1 is in B, so we're going to keep the top half of this column the same, but we're going to turn the bottom half into 0. Similarly for V2, same idea. But then for V3, It's not in this basis, so we're going to turn the top half to 0, and the bottom half is going to be just 1. Stay what it was here. And you can see that I do this for each of the 3 bases. The bases of this are just any set of 2 columns. And I encourage you to pause and look at this slide for a little bit to really understand where these are coming from, because this is super important for my theorems. And then what we're going to do is take these parallelepipeds and take the union of them, and we're going to call this the tile associated with D. And there's a good reason why we call it the tile, but I'm not going to spoil it yet. So in this case, we have these 3 parallelepipeds, and here's a drawing of what they look like. The first one is the cube, the second one is the smaller rectangular prism, and the third one is the larger rectangular prism. And we're just going to put them all together, and this is going to be what we call our tile. All right, time for some exciting theorems, but first a not particularly exciting definition. The continuous sandpile group of D is going to be the set of real numbers divided by D transpose time, or curly D transpose times Z to the n plus R. So what is this? This means, and if you recall the sandpile group, we just replaced R with Z. This is saying that you can get any points in space and talk about whether or not they're equivalent with respect to the continuous sandpile group. And they are if and only if you can get from one to the other by adding some integer linear combination of the rows of curly D. So here's a cool theorem. The interiors of each of these parallelepipeds do not intersect. So we can see in this example, we have 3 different pieces and they intersect at the boundary, but they don't overlap each other at all. And furthermore, even more amazingly, any 2 points on the interior of our tile are distinct as elements of the continuous sandpile group. And this might not be immediately clear why this is important, but it's really great. And these 2 theorems, I would love to explain how to prove them because it took me so long. And then finally I came up with a proof that was so much more elegant than a lot of the avenues I was looking at, but I just don't have time for it. So look at my paper if you're interested, because they're pretty great. But then there's some other stuff, some more exciting theorems, so we can actually get to the final construction. For each basis, the volume of the parallelepiped is its multiplicity squared. This is related to the fact I said earlier that if you restrict to some columns of D and restrict to the remaining columns of D hat, you get the same determinant. But using that, you can work this out pretty quickly. But then what this means is that the volume of the tile, because none of the pieces overlap, the volume must be exactly the sum of the multiplicity squared. And if you recall from the cellular matrix-tree theorem, this is the size of the sandpile group. So we have a tile that's the same size as the sandpile group. Furthermore, if we take this tile and we translate it by some integer linear combination of the rows of curly D, that gives a non-overlapping tiling of R to the n, R plus n. And this follows mostly from the last theorem on the last page, but it's pretty great. And it's gonna really help us prove what we wanna prove. So let me give an example of this so you can see what's going on. So I'm gonna let n and R both be equal to 1. This way we're tiling 2-dimensional space, and I can draw it. So curly D has to be of this form, where you have 1s in one diagonal and then k and negative k in the other one. Remember, D is the top part and D hat is the bottom part. And when k equals 3, it's going to look like this. So you have your 2 squares, the squares of the parallelepipeds in 2-dimensional space. And the first basis is associated with this square, the second basis is associated with this square. And if we translate these by integer linear combinations of the rows of curly D, it's going to tile the whole plane. So it's going to look like this. And furthermore, let's look at this a little bit more closely and we can get even further. What I want to do is take each point in Z2 and associate it with some basis. So the most obvious thing to do is to take the points that are inside some parallelepiped and associate it with a basis that that parallelepiped goes with. So these 4 points are going to go with our second basis. But the points that are on the boundary are a little bit more complicated. How do we deal with those? So what we're going to do is we're going to choose a direction, some generic direction, and we're going to nudge all the points in that direction and see where they end up. So now we have these 9 points that are going to be nudged into this bigger square, and we have this 1 point that's going to be nudged into this little square. So why am I doing this? Well, in fact, this construction always maps multiplicity squared points into each parallelepiped. So in this case, we had 1 was the multiplicity of the first basis, 3 is the multiplicity of the second. So we had 1 squared vectors go into here, 3 squared go into here. And you can show that these are actually all different elements of the Sandpile group. These are like, the Sandpile group is size 10 in this case, and this is 1 representative from each equivalence class. So pretty cool stuff. And this works in general also. So that's what I'm going to be talking about here. We get to the conclusion already. For any standard representative matrix and a choice of generic direction, we can construct a natural map such that the preimage is exactly what we want. And just to remind everybody, we did this by first constructing a polytope for each basis, and then we combined them to form our tile, and this periodically tiles our R plus n. And then we're going to shift each lattice point slightly in the direction of W and see where it ends up. And something interesting about this is that the maps actually specialized to the ones given by Backman, Baker, and Yuen. They did the case where you have a regular matroid where all of the multiplicities are 1. But it doesn't, there's a lot to show here. It's not obvious that these are the same and that the constructions are very different. So you have to do some work to show that it does in fact specialize. And finally, I want to show you some pretty pictures. So I'm not going to go super into detail on how this works, but based on the structure of curly D, we can actually tile R to the R or R to the N instead of R to the R plus N. And that means that with R equals 2 and N equals whatever, we can get a tiling of R2. So in particular, here's an example I did in Sage. In this case, when we go down to the lower dimension, instead of getting 1 parallelepiped of size multiplicity squared, we get multiplicity many, each of size multiplicity. So it ends up being the same total volume. But in this case, all of the stuff that's the same color is associated with the same basis. And in fact, you can see how this tiles the plane right here. This is 9 copies of it. And then I'll show you the same thing for another one, maybe even a prettier one. This is the one that comes from this matrix, and this is what it looks like tiling everything. So thanks so much for listening. Here's this shape again. If you have any questions, you can email me at this email. One thing I want to say before I'm done, now we've explored enough to realize that this is a really cool shape because it actually periodically tiles space. And as soon as COVID dies down a bit and I can figure out how to 3D print stuff, I'd love to 3D print a bunch of these and put them together and play with those. But for now, you just have this picture of perspective drawing. So yeah, thanks again. Hope you enjoyed the talk. And yeah, thanks again to the organizers for inviting me.